All right, so I'm going to take a look at section 9.4, and this is our last section. And what we're looking at are hypothesis tests again, but this time we're looking at working with hypothesis tests for mean. So making a decision about what we think is true or is not true for a population mean based on a particular sample that we select. So the process is exactly the same as it was back in chapter 8 for running a hypothesis test. Step 1, you're going to make your hypotheses. So that, just like always, that would be your null and your alternative hypothesis. And then step 2 is to prepare, check your assumptions. Now, we didn't do a whole lot with checking those assumptions for the central limit theorem, but it is an easy check, so we'll look at that in this lesson. Step 3 is to compute your test statistic and your p-value. Now, I have a formula here to calculate the test statistic. This time we're going to call it a t-test instead of a z-test, like we did back in chapter 8. You're not going to have to compute this by hand, however. I will give you the information either from a screenshot in StatCrunch if it's on a test, or you'll just use StatCrunch if it's in one of the homework questions. And then interpret. Decide based on that information, based on your t-test and the corresponding p-value, whether you're going to reject the null hypothesis or fail to reject it. So this time we're looking at a t distribution instead of a z distribution. And so we call it a t-test, or a test statistic using t as our symbol. And the notation that we would look at is x bar minus mu naught divided by the estimated standard error. And the estimated standard error is found by s divided by the square root of n. So what does all this mean? So let me zoom in a little bit here. X bar is going to be the sample mean. So remember, you're pulling a sample and you're going to calculate the mean, or they'll give you the calculation for it. That's going to be your x bar. So your x bar is going to be your sample mean. And then going along with that is S. That is your sample standard deviation. Those will either be given to you in the question or you'll use StatCrunch to calculate them. So you're going to pull a sample from the population and you're going to calculate its mean and its standard deviation. N, just like always, is your sample size. And then mu naught this time is going to be the mean for your null hypothesis. So you're going to write your null hypothesis that the population mean is the same as some other previously calculated population mean that you're made aware of in the problem, and that number you're comparing it to is mu naught. If the conditions hold, and we'll talk about what those are in a second, this follows a t distribution with degrees of freedom of n minus 1. So what are the two conditions that must hold in order to run a hypothesis test for mean? Well, the first is that it has to be a random sample. It always will be. We'll always tell you the sample was pulled randomly. And the observations have to be independent, and we can assume independent. In other words, each person in your sample has nothing to do with anybody else in the sample. As long as it's random, you can assume that they're independent. And then the other condition is that you have to have a large sample. And how large does it need to be? It needs to be large enough that you have at least 25 observations in your sample. So 25 or more have to be in your sample. So let's look at an example here. In 2010, the mean years of experience among a nursing staff was 14.3 years. So that's our previously defined mean for the population. A nurse manager took a random sample of 35 nurses at a hospital and found a sample mean of 18.37 years and a standard deviation of 11.12. So the 18.37 and the 11.12, those are calculations on your sample. I'm going to jot a few things down here. I think that's a good idea. Anytime you read a question, start writing some things down. So the 18.37, that's going to be your X bar. That goes with your sample. And then the 11.12, that's going to be your standard deviation. That goes with your sample. We know that there are 35 nurses in our sample, so that means N is going to be 35. And then what is this 14.3? That's what we're going to use for a hypothesis. That's what we're going to compare everything to, is that 14.3 number. So that's your mu naught, 14.3. Okay, so looking at these symbols back up here, that's your mu naught. The question we want to evaluate is, do we have evidence that the mean years of experience among the nursing staff at the hospital has increased? So just like always, that phrase is going to tell you how to set up your alternative hypothesis. So let's write down our hypotheses. So our null hypothesis, and make sure you use good notation for this, H naught, and then instead of P, because we're not doing a proportion this time, we're doing means, I'm going to say mu is still equal to 14.3. Nothing has changed. The mean number of years of experience for all nurses at this hospital is still 14.3. The alternative, just like always, is based on the way the question is phrased. In this case, it says has increased. So we're going to say mu is greater than 14.3. The prepare step, let's go ahead and just verify that the two conditions above are met. First, they told us it was a random sample, and they did. So it's a random sample, and by that we can assume independence as well. And is the sample large enough? Yes. How large does it need to be? It needs to be at least 25 observations, and it is because n is 35, which is of course more than 25, so we are good to go there. Sample's large enough. All right. Compute would be the StatCrunch part. Now there are two ways you can do this in StatCrunch, and I'll show you this because I'm using the computer in the classroom, so I have access to StatCrunch here. There's two ways you can do it. The first way is to go to the T-Stats menu. The second way is to use the calculator and use a T-distribution calculator, which is what I have a screenshot for here. I'll show you both ways in StatCrunch so you can see the difference. So I've got a window here for StatCrunch. So doing it the first way, make sure we're still recording here. We are. Doing it the first way, I'm going to go to Stat, T-Stats this time. Remember in chapter 8 we did proportion stats. Now we're doing T-Stats because we're looking at mean instead of proportions. And I'm going to go to one sample. I'm going to type in with summary. I'm going to type in the data myself. I'm going to go with summary. All right, so then my sample mean was given to me earlier in the problem. My sample mean back here, remember that was the 18.37 number. My sample standard deviation was also given the problem, that was S. My sample size is 35. And then your hypotheses, you're going to set those up just like we always do. We're going to use our null hypothesis. This time notice it's mu because we're looking at means. So mu, and it defaults to 0, so I'm going to put in mu equals 14.3. And then my alternative was that it was greater, that the mean was greater than 14.3, so I'm going to put greater than. And then I'm going to click compute. And here's your information that we need to answer the question and make a decision about our alternative hypothesis. So notice what do we notice here that's similar to what we had in the last chapter, in chapter 8? Well, the mean, the standard error, you don't have to do anything with that right now. The standard error is actually calculated using this formula back here, but we don't need that. That's just information done to calculate the p-value. Test statistics, same thing. That's this formula back here. I won't ask you to do that by hand. But it's just like when we look at a normal distribution. We want to know how unusual this value is. T-stat or T-statistic here is 2.16. And the p-value that goes with it, that's how we're going to judge whether or not that's an unusual or an unexpected value, is by looking at this p-value of 0.0187. Now, just like we did back in chapter 8, we're going to compare that p-value to our significance level. Our significance level, alpha, in this case, is 5%. Remember, we can always use 5% if they don't give us one. So I'm going to go ahead. I'm just going to use that p-value of 0.0187, and I'm going to compare it to that 5%. All right, so what does that mean? Let's write some things down here. So our p-value from StatCrunch, pull that up again, our p-value was 0.0187. 0.0187, and notice that that is less than our significance level. Our significance level was 5% in the original question, okay? So remember what that means. When the p-value is small, that means we reject the null hypothesis. So in this case, we're going to reject the null hypothesis because our p-value is below our significance level. By the way, this screenshot you're seeing with this alternate method in StatCrunch to get this information, let me just show you what that looks like in StatCrunch. We would go, let me close this out for a minute. We would go to Stat, Calculators. Just like earlier in the course, we used to do a normal distribution. It's the same idea. We're just now going to do a t-distribution. We're going to put in our information from there. So I'm going to put in my degrees of freedom. Remember, it's n-1, so my n was 35, so it's going to be 34. And I'm looking for the probability that we are greater than our t-score. Now, here's where this is probably not the best method if you're relying on the technology, is you've got to know what that t-score is. That t-score I got from StatCrunch using the other method. Let me go back to it for a minute. Yeah, here it was. So that t-score of 2.165 is what I would have to put here. This is probably a little bit less convenient if you don't want to calculate that t-score by hand. So I would probably use the other method most of the time. But we could calculate this by hand if we wanted to, using that formula given on the previous page. But we're not going to ask you to do a test or anything, so I'm just going to go ahead and click compute. But I want you to see this is the same p-value right here. So this is the probability of getting a particular sample where the t-score is 2.165 or something more extreme. Remember, if the null hypothesis is true, this is the likelihood of getting your particular sample. So because that likelihood is small, it's less than 2%, that leads us to think that the null hypothesis probably is no longer true, so we reject the null hypothesis. And that's where our interpretation is back here. So let's go ahead and write some things down. So we're going to say since the p-value is small, we're going to reject the null hypothesis. This means we have evidence to support the alternative, and the alternative was what? The alternative was that the mean number of years of experience for these nurses has gone up from 14.3. That's what we're going to say. Support the alternative that the mean number of years has increased from the 14.3. The logic you're using to solve these problems is the exact same as the logic you were using back in chapter 8. We're going to run the hypothesis test. We're going to look at the p-value. We're going to make a determination on whether that p-value is small, and based on that, we're going to decide to reject the null hypothesis or not reject the null hypothesis. And then we're going to make our conclusion from there. The only thing that's different is the distribution is different. Back when we were looking at proportions and we were using the central limit theorem, we were essentially using a normal distribution for everything, and that's what we were working with. This time we're working with what's called a t-distribution, but the logic is the exact same logic as we were using in the previous chapter. So all of that should feel very comfortable for you in terms of whether or not we're rejecting the null hypothesis, where we're getting that number, and how we're making that decision. So as far as whether it's a two-sided test or one-sided test, everything's the same as it was back in chapter 8. So the two-sided test, that's when your alternative hypothesis is not equal to. If it's a left-tailed test, we say that your mean is less than whatever mean you're comparing it to. A right-tailed test, we say that our mean is greater than whatever mean we're comparing it to. Let's do another example. In the 2010 season, average home attendance for hockey games was 17,072. So I'm going to write that down because that is my mu naught. That's what I'm going to compare it to. That means my mean from my previously calculated, what I think is true for the population, is 17,072. Suppose a sports statistician took a random sample of 30 hockey teams. And by the way, I really want you to write something down. When you're doing these problems in my stat lab, you need to get paper out and you need to be writing these things down. As you read through the question, write down the information that you're coming across, because that'll help you keep everything straight when you're ready to work the problem out. So 30 hockey games, that's your random sample. So that means n is equal to 30. During the 2014 season, and they found that the sample mean was 18,104. So that means x bar is 18,104, and your sample standard deviation was 1203.5. Now, it could be a situation where they don't give you this information outright. Maybe it's a smaller sample. Maybe it's where I give you a bunch of data and you've got to calculate the sample mean and the sample standard deviation. You probably use StackCrunch to figure that out. I'm not going to ask you to do that by hand. But when they give you the sample mean and the sample standard deviation, it makes it a little bit easier because you've got that information readily available and you can go ahead and run your test based on that. So the question says, can we conclude that mean attendance at hockey games has changed? So based on that, we can go ahead and set up our hypotheses. Our null hypothesis, again, good notation, you're going to say H naught colon, and then not using P now, we're using mean. So we're going to say mu equals the assumption nothing has changed. It's still 17,072. Your alternative, so H sub A with your colon, is that the mean is changed. So we're going to say not equal to 17,072. Okay. All right. So the prepare step. So the two things that have to be true, it has to be a random sample, which they told us in the problem it was, so we can also assume independent observations. And then it has to be large enough to be at least 25. Well, my hockey game, I see my sample was 30. I had 30 games that I looked at. 30, of course, is more than 25. So we're in good shape. All right, so now we can go ahead and do our test. So I'm going to use, here's a screenshot of it, but I'm going to show you again what this looks like in StatCrunch. So go back to my StatCrunch window here. All right, so I'm going to go, remember how to do this. We go to Stat, and then we go to T-Stat, one sample with summary. My sample mean was 18,104. My sample standard deviation was 1203.5, and my sample size was 30. So my null hypothesis is that P was still equal to 17, or not P, sorry, mu was equal to 17,072. My alternative was that we are not equal to that for the mean, so I'm going to click compute. And here's what I have. Okay, so this is exactly what you have on your piece of paper there. There's your information. So I'm going to close it out this window for right now. Notice that my t-score is 4.696. That's pretty unusual, I would say, and the p-value that goes with it is very small. So this is an extreme test statistic, which means I have a very small p-value. That's what you want to remember. Extreme test statistics leads you to very small p-values. So what does that indicate? We're going to do what? It's a very small p-value. They did not give us a significance level of, but it doesn't matter. We would always default to 5% if they don't give us something. But really, in this case, it's not even a big deal. Because look how small your p-value is. It's 0 for all practical purposes. So I'm just going to say, note that our p-value is very small, which indicates that we're going to, once again, reject the null hypothesis. So interpretation, since the p-value is small, we reject the null hypothesis, which means we have sufficient evidence. I'm just going to say we have evidence that the attendance, or I should say the mean attendance, sorry, this is a little messy, the mean attendance at all NHL games has changed. What has it changed from? The original mean that we thought it was, we were comparing it, remember, to that 17,072. So it has changed from 17,072. It'd be interesting to run this test today, seeing as we're in the middle of the pandemic. But imagine it's changed quite a bit since then even. For the data we had from whatever year this was, 2014, we've changed from that original number we projected from the 2010 season. That's what we're saying. All right, so let's take a look. I think I've got one more example here. So this last example, it says, recall the example asking whether the mean cost of two-year colleges has increased since the 2008-2009 academic year. In 2008-2009, the mean cost of all two-year colleges was $25.17. So since they're talking there, I'm going to use different color here. Since they're talking there, for the mean cost of all two-year colleges was that number. That would be your mu naught. That's what we're going to compare everything to. 25.17. So all colleges. So that's your population mean, or what we think was true about the population mean before we took this new sample. Our data are a random sample of tuition prices at 35 two-year colleges. So that means N is equal to 35. From the 2012-2013 academic year. The sample mean for our sample of 35 colleges, our sample mean is 2918, so that would be X bar. And our sample standard deviation was 1079. Test the hypothesis that the mean tuition cost of all two-year colleges has increased. Okay, so I would pause the video at this point and go ahead and write these things down and then check back with me and see if you got it. So our null hypothesis is that nothing has changed. The mean is still 25.17. The alternative is that the mean, it said, has increased. So I'm going to say that the mean is greater than 25.17. Prepare, we were told that it was a random sample. So we have a random sample, and by that extension, we can assume independence. And then is our sample large enough? Yes, it is, because our sample has 35 schools in it, which is certainly more than the 25 that's required. So let's go ahead and do our computation. I didn't put a screenshot here, so I'm going to go ahead and get this information from StatCrunch. All right, so here it is. We're going to go stat, t-stat, one sample with summary. All right, so my sample mean was 2918, so that's X bar. My sample standard deviation was 1,079. So in other words, of the 35 schools that I randomly selected, this is what I found. The mean for that sample was 2918. The standard deviation for that sample was 1,079. My sample size, I selected 35 schools, so I'm going to type that in. So my null hypothesis is that mu is still 2517, and my alternative is that mu is greater than that. I'm going to go ahead and click compute, and let's see what we've got. So my p-value, it's interesting, all of these I had very small p-values, so that meant that I reject the null hypothesis again. P is 0.0174. It's a very small p-value, although they did tell me to use a significance level of 5%. I'm certainly within that tolerance. All right, so write some things down there. Make sure you got that on your notes there. So your p-value is 0.0174. That's the part you really want to pay attention to when you're making your decision about whether or not to reject the null hypothesis. So we're going to write some things down. So our p-value was, I forgot what it was already. This 0.0174. 0.0174, which is definitely small. Smaller than our alpha of 5% up there. So how are we going to interpret this? We're going to say, once again, we're going to reject the null hypothesis. So we're going to reject the null hypothesis. That means there is sufficient evidence, probably no surprise to you, tuition has gone up, sufficient evidence that mean tuition for all, I can go back and reference your population. Who are you talking about? You're talking about all two-year colleges this time. So all two-year colleges has increased from, what number did we say it increased from? That's from our null hypothesis. That's our mu naught, 2517. Now, this doesn't tell us what it's increased to. Remember, that's what we did in the last section. We did a confidence interval, and we said, okay, what do we think the population mean is? And we came up with an interval for a confidence interval based on our sample. This time, we're just doing a hypothesis. So all we're saying, we're back to the yes or no question. All we're saying is, do we think the sample or the population mean has increased from that original number? And based on this evidence, it does look like that is the case.